Welcome. This is our fourth class. This class will deal with the topic of multiple regression. So last class was simple regression. We only had one variable, or one predictor variable. This time we're going to have more than one predictor variable, although we won't have any interactions. But we'll have more than one predictor variable. Okay, we're going to start probably a little repetitive or going over what we've already talked about. But again, of course, multiple regression is based on the linear model. And we can ask, what is the linear model? And as we said last time, the linear model is just a way of predicting the value of one variable from another. It's a hypothetical model, the relationship between two or more variables. The model used is a linear one, and therefore we describe the relationship using the equation of a straight line. And of course, what I would add to what Fields says is that although we use the linear model for prediction, we also, of course, use it for theory testing and understanding. And a lot of times that's where the issues actually come in, not purely with whether we can predict or not. So again, a simple model, in the simple, again, regression model that we had before, as we talked about last time, we have some outcome variable, y, and this would be the y value for one subject, participant, case, whatever you want to call it. And it's going to be equal to, in parentheses, the b weight for the constant, which is really, it's just going to be a single number, and it's just the concept, constant. And that's also then an intercept, or the value of y when x is 0, or the point at which the regression line crosses the y-axis or ordinate. And then we have, in the specific case of a simple regression, a b1 times our predictor variable, or independent variable, x. And of course, again, this is an x for particular observation on a particular case. And so that's basically our model. And then to that, we add error, and that gives us the individual's observation. And again, then this B1 represents the coefficient for the predictor. It represents the gradient or slope of the line, and it represents the direction or strength of that relationship. So again, beta or B values. Again, when we go to multiple regression, of course, we're going to have more than one predictor variable, and we just number them consecutively. So B1 would be the coefficient for variable 1, B2 will be the coefficient for variable 2, and all the way up through B sub n, which would be the coefficient for the nth variable. And of course, what we're basically doing is creating a regression line. And that regression line has a certain degree of fit in the sense that there's a distance between the predicted values and the observed values. And of course, again, we can calculate total error as the sum across all the subjects of our observed values minus the predicted or model values squared. So it's basically that error term squared. And again, we can estimate the fit of the model because, again, the model is based on the data, but it may not perfectly reflect reality. In psychology, it's very rare it even comes close to reflecting reality. So we need some way of testing how well the model fits the observed data. And usually that's a combination of our F ratio, whether it's significant or not, and our R squared, and how high our R squared might be. And again, then we went through last time how Field labels these. Field labels these SST as being the difference between the observed data and the mean value of y. SSR, the difference between the observed data and the model. And then SSM, the difference between the model and the mean value of y. So SSM, the difference between the mean value of y and the model. So a brief summary again, SST is the total variability, the variability between scores and the mean. SSR is the residual or error variability, the variability between the model and the actual data. And then SSM is the model variability, the difference in variability between the model and the mean. And again, that's how field labels them. It's a little bit of an unusual labeling, but that's how field labels these sum of squares values. And as we said, a lot of people might call actually what he calls SSR, SSE, or error sum of squares. And then a lot of people might call what he calls SSM, SSR, or the regression sum of squares. But again, you know, it's like naming your pet or naming yourself. You can pick what name you want to give things. Technically, you can pick any way you want to name a variable in a, or a parameter in a statistical analysis. And then, of course, we test for fit using the F statistic. And the F statistic we get, again, the SST is made up of the SSM, and the SSR. So SST equals SSM plus SSR. And if the model results in better prediction than using the mean, then we would expect SSM to be large or big compared to SSR. But what we really do, of course, is we calculate our mean squared errors first. Sum of squares are total values. We want to calculate sort of averages or mean squares. So we divide by the degrees of freedom to get our mean squares. And then our F value or F ratio is going to be the mean square for the model divided by the mean square for the error term. And that'll give us our F ratio. Then we can determine the significance of that F ratio. We can also get R squared in the case of a multivariable model. Well, in all cases, it's going to be the proportion of variance accounted for by the regression model. It's going to be the Pearson correlation coefficient squared, or another way to express it, R squared is going to be the sum of squares due to the model divided by the sum of squares total. And then we're going to get a T for every B. So if we have 20 variables, we're going to get 20 T's plus 1 T for the constant. And we calculate our T by just taking our B observed minus our B expected over the standard error of B. And that gives us B observed divided by the standard error of B, because B expected is going to be 0 in most cases. It doesn't have to be, but in most cases, we're going to hypothesize a 0 value for B. So B expected would be 0. So B observed minus B expected is going to give us B observed, since a number minus 0 is the number. And then we just divide by the standard error of B to get our T value. And then again, we'll note that Field goes through and he gives you sort of a flow chart for when you should in fact do regression and maybe when you should use some other type of approach. And we went through this last class. I'm not going to repeat it now, especially because these classes get long enough as it is. Okay, so again, there's some straightforward assumptions we can make in terms of variable type. As we said last time, the outcome variable, the y variable, is usually going to be continuous. It doesn't have to be, even though he says that's an assumption. Because again, if it's not continuous, if it's dichotomous, especially, we're probably going to run a logistic regression. But the predictors can be either continuous or dichotomous, or they can be categorical. But if they're categorical, then you need to code them in some way to put them into the model. Non-zero variance, that's sort of a given. Your predictors must not have zero variance. If they have zero variance, they're not going to predict anything. Linearity, the relationship we model is in fact linear, and that's usually a pretty safe assumption also. Independence, and that's that all values of the outcome should come from a different sort of group of people, or uh, a different panel of raters, or a different group. So it should come from different individuals. There shouldn't be correlated errors between those observations. If there are, then we move on and do a multi-level analysis. And of course, one of the things we can start with, of course, this is from Field's example. He suggests starting by doing a scatter plot of the data. So we're going to be using it. We're going to again start by going through his example, and he has a number of variables in his example, which uses album sales. He has album sales, he has advertising budget, he has number of plays on the radio, and he has a band image rating, which goes from 0 to 10. I guess it could be a brand image rating also, but a band image rating that goes from 0 to 10. Okay, so again, his example, it's a musical example. A record company boss was interested in predicting album sales from advertising. The data, there's 200 different album releases. The outcome variable is sales, CDs, and downloads in the week after release. The predictor variable is the amount spent promoting the album before the release, or the predictor variables, I should say, are going to be the amount spent promoting the album before the release, the number of plays on the radio, and the image of the band. And of course, we can present this model as an equation. With several predictors, the model is described using a variation of the equation of a straight line. I note we've cut off E at the end here for my picture, but basically the line or the model is going to be that our Y, or our predicted value, or the value we're trying to predict, the dependent variable, is equal to some constant, that's your B sub 0, plus B1 or B sub 1, the B weight for the first independent variable. So in this case, it's B1 times X1, plus B2, B sub 2, the B weight for the second independent variable, in this case B2 times X2. And that goes all the way through however many variables you have, all the way through N. So all the way through Bn times Xn. And the I just tells us that we're doing this for each case. In this situation, there's 200 albums. We don't need the cases to be people. The cases are those individual album releases. And so I would be those cases from 1 to 200. And then since this is predicting an individual observation, or for one individual, their Y value, we would have an error term at the end that's sort of cut off. As Field says, unless you're really special, I guess there are some people that can think in 3 or even 4 dimensions. I don't know, if you can think in 3 or 4 dimensions, raise your hand, or 5 dimensions or more dimensions. It's hard to think and graph things in more than 2 dimensions. Maybe 3 dimensions you can do, but getting like 4 or 5 dimensions gets pretty tough. But so if we have 2 predictors, we have a model that's really in 2 dimensions. The regression, the scatter plot, and your regression analysis is occurring then in a plane, right? It's sort of, instead of a line, it's sort of a plane. And so he's trying to graph that here and make it visual for you. Again, I'm not a very visual person, but here we can see that he's trying to show you what the model would look like when you're trying to predict, again, album sales from 2 predictors, the 2 predictors being plays on the radio and the advertising budget. But in this case, we're doing it from 2 variables instead of 1, And so we can visualize that from a geometry perspective as occurring on a plane, not a PLAIN plane, but a plane, and not a plane that flies, but a plane, so to speak. Of course, we start off, we have our b sub 0. That's going to be the constant, right? So that's still the intercept, no matter how many variables we have. The intercept is the value of the y variable now when all your x's are 0. Excuse me. And it's the point at which the model plane crosses the y-axis, or the vertical axis. Then again, you have beta values. Again, I don't like the use here of beta values because I think betas refer to the standardized values, but as long as you understand he's talking about really the unstandardized b's, the little bb's. And so little b1 or little b sub 1 is the coefficient for variable 1. Little b2 would be the coefficient for variable 2. And little bn sub n would be the coefficient for our nth variable, however many variables we're including in our model. Okay, building the model. This is part 2 of his. This isn't part 2 of ours. We're still in part 1 of our lecture for today. So when we build the model in SPSS or whatever we're building it, we actually have a lot of choices. There's probably even more choices now. Field doesn't really get into some of the more esoteric or exotic approaches to regression that are available. And we're not really going to get into this class because we're already pretty full up in this class. But there are newer, more, I think esoteric is the best word, approaches to regression. We're not dealing with those. So we're going to deal with the typical, sort of the old-fashioned, I guess you could call it, approaches to building a model in regression, the choices of approaches to building a model. All right, we'll start then with what Field calls hierarchical entry. Hierarchical entry is when we have known predictors based on past research that are entered into the regression model first. Or there may just be logical reasons. I don't think you have to have past research. There may be logical reasons for entering certain variables first. For example, maybe they're control variables, which we'll talk about later on. And then new predictors are then entered in separate steps or blocks. So some people call this like a 4-step entry. The researcher makes the decisions on where and when things are entered. Hierarchical entry is probably sort of a fancy name for what you're doing. But again, all you're really doing here is you're making a choice about which predictors go in at which step. So that's really all you're doing. Okay, so hierarchical entry. Fields actually argues it's the best method. He may be right. He argues it's based on theory testing, and that the advantage is you can see the unique predictive influence of a new variable on the outcome because new predictors are held constant in the model. So you have to understand with regression analysis, once a variable is entered in the model, it's being held constant when you enter other variables into the model. At what point it's being held constant is sort of an interesting discussion, but it's basically being held constant when you enter new variables into the model. Okay, so when you do regression and you do it with hierarchical entry, or really any kind of entry, if there's already a variable in the model, then as you add other variables into the model, the new variable is being held constant. The old variable is being held constant while you're entering the new variables in. Another way to look at that is that you're controlling for the variance. If you have two variables, x1 and x2, and you've already entered x1, when you enter x2, you're controlling for the variance in x2 that's due to x1. Of course, as Field notes, it relies on the researcher knowing what they're doing. And also, I would probably note or add in here, that a lot of people probably do this in an exploratory fashion. So Field is sort of trying to argue this should be really almost confirmatory, or it should be based on previous research or theory, which is a good idea, but probably the way people actually use it is almost in a very exploratory fashion. So they often just look at their correlation matrix, start by entering the most highly correlated variable first, and then try to enter the other highly correlated variables in additional steps, see if that works. If it doesn't work, they just change what they're doing. So, I mean, when we're saying this is the best, it's probably the best if you're actually doing it correctly in a confirmatory way and following some theory or some past research in doing this. Some of the other options, there's an option called forced entry. Um, Forced entry just means you're really just forcing all the variables in at once. Chris, I said before, you could almost see hierarchical regression then as being a forced step entry, because you're forcing the variables in at different steps. But when we talk about forced entry, we're usually talking about you forced all the variables in to the model at that first step. Every variable goes in at the first step. So, of course, the result obtained then depend on the variables entered into the model. So it's important to have good theoretical reasons for including a particular variable. Again, I don't think that's typically true. I think typically people just throw a lot of variables into a model and see what happens. Backward and forward entry. These types of entry are exactly what the name suggests. With backward, you basically force everything in and then you remove things, looking for a better solution. With forward entry, you basically let the software or the computer start by putting in the first variable, then selecting the best second variable, putting that best second variable in, then finding the best third variable, putting that best third variable in. So forward entry, you're really just letting the computer make the decisions. It makes the decision based on what's the next best variable to enter in to the model. And of course, then we have stepwise regression, and that's really a combination of backward and forward, or forward and backwards. It does both. It starts by going forward, but at each step, it takes a look to see whether it should go backwards and remove something. So stepwise is really just a combination then of forward entry and backward entry, doing sort of forward entry first, but then after it does the forward entry, sees if any backward removal is necessary. Stepwise used to be the approach a lot of people like to take, so I mean, stepwise, a field doesn't like stepwise, but stepwise used to be a very common approach because you're letting the computer sort of build the best model. I mean, you can almost look at it as, simple machine learning or simple artificial intelligence. The computer or the software is picking the best variables and the best model based on certain rules. Okay, so stepwise entry then, variables are entered in the model based on a mathematical criteria. The computer selects the variables in each step. So if you think about it, especially for example, SPSS, in step one, it looks for the predictor that can explain the most variance in the outcome variable, and it enters that. Then in step two, having selected the first predictor. A second one is chosen from the remaining predictors. What it does is it looks for the best semi-partial correlation. So if you think back to the last lecture or 2 lectures ago, whichever one it was when we discussed semi-partial correlations, it looks for the best semi-partial correlation given you're controlling for the first variable and selects the best semi-partial correlation for the variable to enter at step 2. Of course, then it would go backwards. It would take a look to see if either one of those variables would need to be removed. Then the next step, it would enter the next best semi-partial correlation, controlling for the first 2 variables. After it enters that, it would then look to see if any of the 3 variables it's already entered need to be removed. Okay, according to Field, the problems with stepwise entry are a reliance on a mathematical criterion. Variable selection may depend upon only slight differences in the semi-partial correlation. And these slight numerical differences can lead to major theoretical differences. So he suggests it should be used only for exploration. But again, I would probably argue most researchers are doing exploration. If that's what he's arguing, then stepwise might be the best in many situations. Also, as I also indicated, you could look upon stepwise as being a sort of very basic type of machine learning or artificial intelligence approach to the selection of the regression model. Okay, so anyway, entry of variables, what can we really say about it? Well, these days, it's a lot more complicated, really. There's a lot of ways of looking at what is, in fact, an important variable. What's really should be the weight of this variable? How should we just judge the contribution of this variable? So there's a lot of other alternatives. You may even want to look at alternative approaches to regression, depending upon what your intent is with your regression analysis. I mean, for example, if your intent is really to look at which variable is the most important, you probably shouldn't be using really any of this. There's alternative approaches. But of course, again, all those alternative approaches also have problems or issues with them. Another issue that comes up, I think this is a good issue or topic, is should you consider correlations before putting data into the model? When I took regression a long time ago, and I took it in a statistics department, so I took all my stats classes from stats professors in a statistics department. They always would probably argue that, at least back then, that you should only put variables into your model which are actually correlated with the dependent variable. So if a variable isn't even correlated with the dependent variable, don't put it into your model. Now, I probably should add to this, though, because this was a stats class, some of the books and even the teaching were oriented towards people in physical sciences as well as social sciences and education. And in the physical sciences, sometimes you're probably more likely to get pretty good correlations, really high R squared. So the issues might be a little different than in psychology, where you might struggle to find variables that really have a significant correlation with the outcome. Nevertheless, I actually think this is a good piece of advice. I think it's a good piece of advice to maybe say, hey, if a variable isn't even correlated with the dependent variable, significantly correlated, then maybe I shouldn't even be including it in the model. Now, it would be different, of course, you're looking at moderators, or maybe even, boy, these arguments get tough when you get into mediators. But if you're looking at perhaps moderators, it might be different. You know, there's also what are called suppression variables, etc. So there's a lot more to this debate. None of these topics are easy, even though we're trying to present them here as pretty simple and straightforward as easy. You know, there's a reason there's PhDs in statistics. And then finally, a variable could always be what's called a suppressor, which means even though it doesn't have, even though it doesn't correlate, it has a suppression effect or an enhancer, or something else weird. So just because a variable doesn't correlate doesn't mean it can't have a significant effect on your overall model. And again, the best example might be if it has a moderating effect. But the fact of the matter is, suppressors and enhancers are very rare. As a matter of fact, I know some people would argue, hey, really in psychology, suppressors and enhancers never occur. So there's really no use looking for suppressors and enhancers. And actually, in this class, we're not really going to get to talking about, I'm not going to talk about suppressors or enhancers, mostly because I tend to be of that belief that they don't really tend to occur anyway. So we're not going to deal with them. We have enough to deal with in the time we have available. Okay, bias and generalization. So again, field suggests, of course, that we start by screening our data, by doing things like looking for outliers. Great advice. So here he shows with this data, one outlier, and then what it does to the regression line. So he's showing you how what should be the regression line, if you get rid of the outlier, is impacted. Here's the regression line with the outlier. How the regression line is impacted by this one really unusual outlier, where the record companies spend a lot of money on the advertising budget, but the album sales were very low. So, that's why it's good in a lot of situations to get rid of outliers. Although, as I said last time, the problem is, especially if you have small sample sizes, is that outlier a real data point? I mean, if it is, what's that telling us? So I always think you have to be careful in making your decisions about what to do about outliers. Influential cases. Influential cases are just cases that would have a really big or huge influence on the regression equation. And so, yes, I mean, you should look for influential cases that have a large or unusually influential impact on the regression equation. Sorry, I left my laser there. That laser wasn't a point. This is your influential case right here. So influential cases are cases that have a large and unusual impact on the regression line. Okay, in terms of screening then, also, I'm not really sure this title is the best. What does the model fit the data? Because that's really your F ratio and your R square. We're talking more here about identifying maybe problem data. And field suggests looking at your residual statistics as a way to identify outliers. So when we look at our residual statistics, we're looking at for our standardized residuals, which we can get SPSS to print out. And basically, I believe field suggests that if a standardized residual is greater than 3, then it's a problematic data point. It's an outlier. He also suggests looking at influential cases. And for looking at influential cases, he suggests using Cook's distance. And again, I believe his suggestion is, please go to the book and make sure I'm correct, but that if a Cook's distance is greater than 1, then it's a problematic data point. Okay, so standardized residuals. Again, in an average sample, of course, 95% of your standardized residuals should lie between plus or minus 2. 99% of standardized residuals should lie between plus or minus 2.5. So an outlier would be any case for which the absolute value of the standardized residual is 3 or more. So if a standardized residual is 3 or more, it's likely you have an outlier in your data. In terms of Cook's distance, that measures the influence of a single case on the model as a whole. And Weisberg, 1982, says absolute values greater than 1 may be a cause for concern. Generalizing the model. Now, again, we hope to be able to generalize the sample model to the entire population, to new situations. To do that, a number of assumptions must be met. Although, again, I think when he's saying assumptions have to be met, meeting the assumptions is more about internal validity, or can we have faith in the statistical results rather than external validity. I mean, external validity, I think, is dependent on a number of other factors. That would be my view. Yes, it's dependent on some of the factors he suggests, but it's also dependent upon a number of the other factors. I really think what he's talking about more is the internal validity, which is usually seen as, hey, can we have confidence in the statistical results? But he calls this generalizing the model and says violating these assumptions stops us generalizing conclusions to our target population. So again, our straightforward assumptions would be variable type, the outcome must be continuous, the predictors must be continuous or dichotomous. Again, if we have a categorical predictor, we really just have to code it, dummy code it in some way. And often dummy coding means we have to create other additional predictors. Non-zero variance, again, the predictors have to have non-zero variance, must not have zero variance. And linearity, the relationship we model is in reality linear, and again, independence. Okay, assumptions that matter in order. Again, additivity and linearity. We're assuming that, if you think about the regression model, we're assuming that each of those estimates can add to each other. If you think it's an additive model, it's a linear and an additive model. Spherical residuals. We assume homoscedasticity, which is for each value of the predictors, the variance of the error term should be constant. So again, if you think about that regression line, you're saying for each point along the x-axis, for each value of the predictor, if we were to plot the scores, the observed scores on the dependent variable, we should basically get a normal distribution. So we should get basically a normal distribution at each point of, or for each value of the predictor for the observed score, or the dependent variable, or the variable that we are in fact predicting. Independent residuals is just that for each pair of observations, the error terms should be uncorrelated. And again, if we have independence, that should be generally true, and vice versa. If our residuals are in fact independent, it suggests that we probably have independence. On normally distributed errors, if we are to plot our errors, they should be normally distributed. No multicollinearity. So if our predictors are too highly correlated, it's going to cause a problem. As a matter of fact, what it often causes, if you think about it, I don't know that Field gets into this in any depth. It often causes an issue where a variable or a predictor that's correlated with the outcome variable, with the dependent variable, with the y variable. So an x that's correlated with y in a positive direction actually ends up with a negative weight. So if two variables, if x1 and x2 are highly correlated, and they're also correlated with y. What multicollinearity often does is x1 will have a high positive b, but x2 will have a negative b. Now that leads to odd situations, right? Because how do you explain to someone that a variable that has a negative weight in the equation actually has a positive correlation with the outcome variable, or vice versa? What you usually the real problem is saying, hey, this variable is positively correlated with the outcome variable, but it ends up with a negative weight in my equation. And so I'm negatively weighting it. This happens, I do a lot of salary research, and this happens in salary studies. Or it might happen, let's say you're looking at, here would be a good example. You're looking at predicting, well, let's say you're predicting salary of faculty members, and you put into the equation two variables. One equation might be their years of experience, and the other variable might be age. So you're putting both age and years of experience into the equation. Now, oftentimes, age and years of experience are going to be almost perfectly correlated for faculty. So you have two variables that are extremely highly correlated. What might happen then is age gets a positive B as a predictor of salary, but experience, even though it's positively correlated with salary, gets a negative B. That's one of the effects of multicollinearity. And now you have to explain to people, well, we're paying you more money because you're older, but we're going to pay you less money because you have more experience. Most people wouldn't be very happy to hear that. But that's one of the impacts of multicollinearity. Checking assumptions about errors. Again, Field takes you through this. I'm not going to I'm not going to try to take you through it in a lot of depth. He suggests checking for homoscedasticity and independence of errors. The way he suggests doing that is plotting your z residuals against your z predicted. We went over that also with the simple regression line. For normality of errors, he suggests a normal probability plot to look at normality of errors. Multicollinearity, again, multicollinearity exists if predictors are highly correlated. This assumption can be checked with collinearity diagnostics. Field suggests that the tolerance, which is one of the indicators of multicollinearity, should be more than 0.2. And the VIF, which is another indicator of multicollinearity, should be less than 10. So that would indicate to you that you don't have multicollinearity if the VIF is less than 10 and the tolerance is more than 0.2. If its tolerance is less than 0.2 or the VIF is more than 10, then you have a problem. And again, here's just that table that we've already shown. I think it's really helpful in Field. It takes you through the process, for example, your initial checks, running your regression, checking your residuals, what the outcomes might be, and what you can do if you get perhaps unpleasant outcomes. And he provides a number of suggestions. Although, again, I think a lot of these statistics are probably more robust to violations than Field is giving them credit for. And the second aspect of this problem, or responding to this problem, is that, as Fields points out, these days with SPSS, it's relatively easy to go ahead and bootstrap your confidence intervals. So if it looks like you have issues, for example, you can see both for heteroskedasticity and for no normality, one of the solutions is to bootstrap confidence intervals. Well, then that's given to you pretty easily by SPSS. So that's a pretty easy thing to get from SPSS. Okay, that brings us to the end of our first half. We'll be back in a couple of minutes with our second half. Thank you.